Right. Welcome everybody to another physics video lecture. Today we are going to be talking about mechanical waves. All right. Now we should start off by talking about what a wave is. Okay. As much as you may see or have seen a wave in your life, you need to understand that a wave is not a thing. Okay. When you look at a water wave, for example, okay, the wave is not the water. All right. When you see a string vibrating up and down, the string is not the wave. Okay. The wave is a disturbance of energy. All right. Or it's a disturbance that carries energy through something. Okay. So the wave is actually energy. All right. Now, there's two major types of waves, and we're going to talk about both of them today. We're going to focus on one, but there are types of waves that move something and require something to move through. For example, like a spring. If I add energy to the spring, I get a wave, right? But there's also waves that can move through nothing, which is kind of interesting. And we'll get there in a second, okay? Last but not least, going back to what I said before, remember that waves are not the matter that they move. Okay, when you look at a wave in the ocean, the wave is not the water. The water is just there. The wave is energy that is moving the water. Okay, so waves are energy that move matter. Okay, they don't transmit matter. Okay, they transmit energy that moves matter or moves nothing, which is pretty interesting. So we'll get there in a second. So examples of waves that I'm sure you know. Water waves are the big example. Sound waves are another type we're going to talk about. And lastly, we're going to talk about light waves. And that's where this whole nothingness comes into play, which is pretty sweet. So let's start off with the big one in the umbrella category for today. We're really focusing on mechanical waves. All right. Now, what does it mean that this wave is mechanical? Well, let's start off by understanding that, again, some waves need to move something and some waves don't. And that's the definition of a mechanical wave, okay? These are vibrations. This is energy that moves atoms, okay? It moves something. And we call that something a medium, okay? You've probably seen the word medium before, like small, medium, large. That's a different definition. Here in physics, when we talk when we talk about mediums, what we mean is it's a substance that something travels through. Okay, we'll talk again about that in the next slide. So let's just keep going here. Okay, the medium that a wave travels through can either be a solid, a liquid, or a gas. We'll see examples of each. And there are two major types of mechanical waves. We have what are called longitudinal waves, also called compression waves, and we have what are called transverse waves. All right. This is a great little slide right here. I recommend pausing, opening it up on your own and reading it, coming back to it. This is awesome. We're going to break both these down in just a second, but this is a nice little slide I made. So let's talk about that idea of a medium again. Okay? Again, a medium is a substance that something is able to travel through. All right. And what this means is that mechanical waves need atoms to move. So I always give this example. There is no such thing as a water wave, right, without the water. If there's no atoms to move, then there's no wave, right? The best example of this, if you ever saw the original movie Alien, which is awesome, the tagline for that movie, I believe, was "In space, no one can hear you scream." And that's true, okay? In order to have a sound wave, you need to have atoms to move, right? In space, right, there are no atoms. Space, is what we call a vacuum, okay? And it's not something that cleans your room. A vacuum in physics is an area that has no atoms in it. There's literally nothing. So you can picture it like an area that somebody sucked all of the atoms out of. It's just an empty space, okay? And if there's no atoms to move, there's no wave, right? When I vibrate this up and down, this is a mechanical wave. okay? The kinetic energy coming from my hands is transmitted into the slinky, and I get a wave, right? If I lose the slinky and I vibrate my hands up and down, I don't have a wave. Does that make sense? Okay. Fun fact about the word medium. Medium is when you pluralize the word medium, since it's Latin, you get the word media, which I'm sure you've heard before, right? Things like social media, okay? Other forms of media include newspapers, books, television stations, radio stations, right? And the reason that we call all of those things the media, all right, is because they are the substance that news and information travels through. That's why the internet is called a media. That's why social media is called media. So it's kind of a fun fact. All right, so mechanical waves need a medium. They need something to move. If there's nothing to move, you can't have a mechanical wave, right? Again, you can't have ocean waves without an ocean. You can't have sound waves without molecules in the air to move. All right, so like I said, there's two types of mechanical waves, transverse and longitudinal. Let's look at transverse first. The difference between the two is how they vibrate, all right? Transverse waves, okay, they vibrate going perpendicular to their motion. What does that mean, okay? What that means is that these are your typical up and down waves, all right? And examples of them, there's a million, but things like ocean waves or electromagnetic waves, these are all transverse waves. So again, when you think of a wave and you think of this, that is a transverse wave. Now, you're probably like, Mr. Norris, you brushed past this whole vibrate perpendicular thing. All right, so the first thing you gotta know is the word perpendicular. We're gonna be using this, okay, a little bit for the rest of the year. Perpendicular, you may see written in math class as this symbol right here, okay? And the reason you do that is because perpendicular means at a right angle or at 90 degrees to something, okay? So if you think about the wave, all right, in this case, our wave is moving to the right. Let's say the wave is vibrating this way. The energy is going this way, okay? Well, the vibration of that wave is going up and down. And again, if the wave is moving in this direction, okay, the vibrations are moving perpendicular. They're going up and down, right? That is more like 100 degrees. But the vibrations are going up and down and up and down, all right? And you can very easily see that if you just watch my hand as I hold this. If I vibrate my hands up and down, I get a transverse wave. Let me see if I can, it's difficult to play with these things. If I just do one side up and down, I get one node of a transverse wave. I have to do both to get more than one node. But as you can see, I'm vibrating my hands up and down, all right? If you walk forward, you can kind of see I'm going up and down, up and down. So again, we're moving to the right and the wave's vibrating up and down, okay? Pretty straightforward. This is super important. Make sure you're taking down these nodes. The other type of wave is what is called a longitudinal wave. And if transverse waves vibrated perpendicular, you may remember the other P from geometry, longitudinal waves vibrate parallel or in the same direction to their movement. Parallel is usually written like this, right? Because they're going in the same direction. Now, these are also called compression waves and or shock waves. I don't use the term shock wave very much. I will use the term compression or longitudinal wave. Longitudinal is a fun word to say. I like saying it. Well, I'll call them compression or longitudinal waves. Examples of these, and the biggest example, are going to be sound waves, but also just your regular old spring, okay? So if you think about it, instead of vibrating up and down, okay, in this case, if the wave is moving to the right, okay, the vibrations are moving in the same direction, which is a little harder to see. That's why sound waves are usually drawn as transverse waves, but they're not. They're compression waves. They vibrate like this. They vibrate in the same direction that they're moving. You see that? So again, watch the difference. This is perpendicular. See how my hands are moving up and down? This, I'm moving back and forth, okay? The wave is moving to the right and to the left. My hand is vibrating to the right and the left, okay? The reason that they're called compression waves is that they compress the atoms. So when a sound wave moves through air, anytime you make a sound, like when I talk, puh, I am pushing the air molecules, right? And right in front of my face, they smush together, okay? And that energy moves forward. So some of those atoms are smushed, which makes some atoms farther apart, which makes these atoms farther apart, and then they get smushed, and it moves forward and forward and forward. And that's how sound waves travel, which is pretty cool, okay? So we got longitudinal waves that vibrate parallel or in the same direction. I always say it like this. Longitudinal waves or compression waves vibrate like this, okay, if they're moving in this direction. Transverse waves vibrate like this. Mr. Norris, what about springs? You've been using a spring for everything. Well, this is a compression wave. Whoa, this is hard to do. If this was a smaller spring and it was vibrating just up and down, watch. I pull it down and now it vibrates up and down, up and down, up and down. It's moving up and down, okay? And it's compressing up and down. So far, so good? All right. So these are the two major type of mechanical waves, and they both move atoms, right? You got to have air to move a sound wave. You got to have a spring to make a spring wave. You got to have the ocean to make an ocean wave. You get it? The other major type of wave is called an electromagnetic wave. Excuse me, we're going to spend a whole day talking about these. In fact, we're going to spend about a week and a half talking about these, but just so you can see the big difference. The major difference between mechanical waves and electromagnetic waves is electromagnetic waves travel through a vacuum. They can travel through empty space, okay? This is super important, all right? Now, electromagnetic waves can travel through a medium, okay? But when they do, the atoms in that medium slow them down. It's like they have obstacles to get past. Electromagnetic waves travel the fastest through empty space. And where do we find empty space? Way up there, in space. They're traveling all through that all the time, okay? Now, that's not to say that electromagnetic waves are not traveling around on Earth. They are, all the time, okay? The way that we classify electromagnetic waves is by the size of their wavelength. We're going to talk about this again in detail, but some electromagnetic waves have a very long wavelength, some have a very short wavelength. We're going to see that that messes with their frequency, and that's the only difference between electromagnetic waves. Examples of these include the light that you see coming off of everything. So the light you see coming off of me, that's an electromagnetic wave. Microwaves are electromagnetic waves. Hopefully you remember that from when we talked about radiation. And X-rays, just to name a few, but there's also infrared waves, radio waves, gamma rays, UV rays. I think I named all of them, okay? And again, we're gonna talk a lot about these. So like I said, these are classified by their wavelength. Some electromagnetic waves have a really long, stretched out wavelength. These include radio waves and microwaves, okay? Some wavelengths have a super, super small wavelength, which are things like gamma rays and X-rays. Right in the middle is where we see visible light, okay? And we are going to talk all about this. So we're going to come back to this and talk about the electromagnetic spectrum after spring break. But just remember this for right now. Electromagnetic waves do not need a medium to travel through. They can travel through empty space, okay? That's how light and heat and UV radiation, light, heat, infrared waves, and UV radiation all get from the sun down to us. They have to travel through space, right? So let's talk about the different parts of a wave. All right, so here we have a transverse wave. It is vibrating up and down. Okay, it's vibrating up and down as it moves to the right, right? It's vibrating perpendicular to its motion at a right angle. Let's talk about all these pieces. The first thing is the origin line, also known as the equilibrium line, and that's this line that goes through here. The easiest thing to think about is if this was a string and it was flat, if it was taut, this would be the string, right? Or the spring. It's hard to make it flat. That would be the equilibrium line. When I add energy, which is up and down, okay, this is now the motion that's moving through. So the equilibrium line is where we started. Again, if this was a water wave, the equilibrium line would be the flat water, okay? Next, we have a crest. Not just a brand of toothpaste, Crest means the top of something, like the crest of a mountain, okay? The crests are the tops. So that's a crest, and that's a crest. We also have something called a trough, okay, which is a weird word. It's not pronounced tro, although it does look like dough. It's pronounced trough, like cough. I hope you don't have one. And the troughs are the bottom of the waves. So this is a trough. This is a trough, and this is a trough. If you know anything about farming, you know that a trough is something that a farm animal eats out of. It's those long tubes. That's why they're called that, because it looks like something that a farm animal eats out of. These look like mountains. Isn't that cool? I would have called them valleys, but that's okay. We also have two measurements, the first of which is amplitude. Very good word. The amplitude is the height or depth of the wave, okay? Specifically, you measure amplitude from the equilibrium line all the way to the top, or from the equilibrium line down to the bottom. This is a very specific measurement, okay? You do not measure amplitude from all the way of the top to the wave, all the way to the bottom. That would be 2 times the amplitude. So it's very specific. It's the distance from the highest or lowest point, okay, to the origin, all right? That's why that's there. And then the last measurement is what is called the wavelength, and this is a very specific thing. Now you may remember this right here. You're like, Mr. Norris, I thought we called that a period. Well, we did when we were talking about time, okay? But if you're measuring the distance between, or the distance of one wave, we call that a wavelength. It's the length of the wave. And just like with periods, you can measure them from any 2 points as long as you go from one side all the way to the other and back to where you started. So you can measure it from here to here. You start on the crest, go all the way to the trough, back to a crest. You could start at the origin, go all the way to one side, all the way to the other side, back to where you started. That's a wavelength. Or you could measure it down here. All 3 of those are equal. They're all wavelengths, and they are wavelengths, so they measure one full cycle, and it's a length, so we measure it in meters. We'll talk about this more when we get into equations, but periods are measurements of time. Wavelengths are measurements of distance. All pretty straightforward. When we talk about a compression wave or a longitudinal wave that's vibrating back and forth, we have what are called compressions, all right? And these are the area where either the spring or the atoms in the air are all smushed together, like right here. This is a compression, okay? They're the areas of high pressure, okay? And we have a word that you've probably never heard before called a rarefaction. Fun word to say, rarefaction. And these are the areas in between the compressions. They're the areas of low pressure, okay? So here you have a rarefaction. Here you have a rarefaction. Here you have a rarefaction. Here you have a compression. Here you have a compression. Here you have a compression. And they are the versions of crests, which are the areas of high energy, and troughs, which are the areas of low energy. And we measure wavelengths the exact same way. You can measure, if you started a compression, you have to start from the compression, go all the way through the rarefaction and back to the same point on the next compression. Or if you start in the rarefaction, start at the rarefaction, go all the way through a compression and go to the next rarefaction, same spot. We still measure wavelength, there's still distances, it's still the same. Okay? All right, guys, that is it for our basic introduction to waves and wave anatomy. Again, if you have any questions, you can email me or find me on Zoom for tutoring. I hope you guys enjoy this, and I'll talk to you soon. Be good.